Hello everyone, welcome to Vyas Edification Kota. In this session we are going to discuss class 12 chapter number 14 Semiconductor Electronics, Materials, Devices and Simple Circuits. Clear? So definitely this session will be very useful to you because we are going to discuss in this session NCERT and exercise solutions. Clear? And actually we will try to understand each and every concept of this chapter with the help of these questions. Clear? So now we are going to discuss each question in a detailed manner. So be ready. Now we are going to start. So dear student, now we are going to discuss question number 14.1. Clear? In this question it is given to you, in an N-type of silicon, which of the following statement is true? Number 1, electrons are majority carriers and trivalent atoms are the dopant. Second statement, electrons are minority carriers and pentavalent atoms are dopant. Third one, holes are minority carriers and pentavalent atoms are the dopant. And fourth one, holes are majority carriers and trivalent atoms are dopant. Clear? So to solve this question or to give the answer of this question, first of all you should know about how this N-type of silicon, or we can say N-type of semiconductor, is formed. Clear? So now you can say, let's suppose if we talk about first intrinsic semiconductor in which we have the 4 valency of a carbon family. Clear? And at the time there is no any impurity present in them. Clear? But what will happen when we add some impurity? Impurity means we are actually adding some atom that is related to third group and the fifth group. Clear? So N-type of semiconductor, whenever I am talking about N-type of semiconductor. So in N-type of semiconductor, actually we can say dopant. Dopant means actually we will mix pentavalent impurity. Clear? So what will happen when we add pentavalent impurity? Pentavalent means we can say like nitrogen, phosphorus, arsenic. So this impurity we are adding in a pure semiconductor. At that time we can say 4 sides of silicon. Let's suppose if I am talking about arsenic. In silicon we have 4 outermost electron. It may bond with it may have 4 covalent bond. So let's suppose it is connected with arsenic like this. Clear? This is arsenic, this is arsenic. But in arsenic we have one more valency because this is pentavalent. Clear? So I can say due to that one, if we provide some heat, all the free electrons will be there in the lattice structure. It means simply we can say in an N-type of semiconductor, dopant is pentavalent impurity. Now what is majority charge carriers? So in N-type of semiconductor you always find majority charge carrier as electrons. You always find majority charge carrier as electrons. Clear? So whenever we have majority charge carrier electrons, what is minority charge carriers? In this semiconductor you always listen about 2 words, hole and electrons. So minority charge carriers and these are holes. Clear? So now let us try to solve this question, or we can say let us try to give the correct answer of this question. In this question it is given, in an N-type of silicon means N-type of semiconductor, which of the following statement is true? Number 1. Now which one is a majority charge carrier in N-type of semiconductor? Electrons. So directly we can say electrons are majority charge carrier. So option number B directly wrong. Clear? And holes are minority charge carrier means option number D is also wrong. Clear? Now trivalent atoms are dopant? No. N-type of semiconductor we have pentavalent atoms of dopant. So I can say which option is correct? Option number C is correct. Clear to everyone? Now we are going to discuss question number 14.2, and in this question it is asking to you which of the statement given in exercise 14.1 is true for P-type of semiconductor. Clear? So let us try to understand. If we talk about P-type of semiconductor, If we talk about P type of semiconductors, In p type of semiconductors we have trivalent dopant. Clear? Trivalent dopant. Clear? Trivalent dopant. And which one is majority charge carrier? Majority charge carrier it is hole. Clear? So in p type of semiconductor you always find holes are the majority charge carrier, and minority charge carrier, for minority charge carriers we have electrons. Clear to everyone? So now let us try to solve which option is correct. So definitely keep in mind holes are majority charge carrier. So concentrate. Now you can say now you can say if we talk about these options A, B, C and D. Now for the p type of semiconductor holes are majority charge carriers, it means option number C is wrong. Clear? I can say option number C is wrong. Clear? And electrons are minority charge carrier means option number A is also wrong. Clear? In p type of semiconductor we always dope trivalent impurity. So directly we can say holes are majority charge carrier and trivalent atoms are dopant. Clear? So now we can say option number D is correct. Clear to everyone? So which one is correct answer? I can say option D. Option D, in which we can say holes are majority charge carrier and we can say trivalent impurities are added as a dopant. Clear? So this is all about question number 14.2. Now we are going to discuss question number 14.3. Clear? In 14.3 it is given to you, we have carbon, silicon and germanium have 4 valence electron each. We know these all are related to carbon family. So carbon, silicon, germanium, so all are having 4 valence electron. Fine. These are characterized by valence and conduction band separated by energy band. Now we know in semiconductor we always understood about band theory. Clear? And in band theory you know we have 2 types of band, conduction band and valence band. So the energy difference between conduction band and valence band, that is known as energy gap. Clear? So now we can say this energy gap is denoted by EGC, EGSI and EGG. Clear? Now we have to find what is the correct statement regarding the order of this energy band. So actually if we talk about energy gap related to carbon, this is given by 5.54 electron volt. Near about you will find this value. Clear? If we find energy gap between conduction band and valence band corresponding to silicon, this will be near about 1.1 electron volt. Clear? And if I talk about energy gap in case of germanium, you will find this is 0.7 electron volt. Clear? So from this data you can see if we talk about energy gap in carbon is more compared to energy gap in silicon than compared to energy gap in germanium. Clear? So now which one is greatest? I can say greatest is energy gap related to carbon and the least one is germanium. Clear? So we can say which option is correct. Yes, carbon should be maximum and germanium should be least. So I can say option number C is correct. Clear to everyone? So this is a correct order. What is correct order? I can say energy gap in carbon, this is greater than energy gap in silicon, and then we can say energy gap in germanium. Clear? So this is correct order. Clear? So this is all about this question. Now dear student, we are going to discuss question number 14.4. Clear? In this question it is given to you, in an unbiased PN junction, hole diffuses from P region to N region. Now first of all let us try to understand what is the meaning of unbiased. Unbiased means, let's suppose we are having a PN junction. What I am saying to you, listen very carefully. Let's suppose I am talking about a PN junction. Clear? PN junction. So let's suppose this side we have P type of semiconductor and on another side we have N type of semiconductor. Clear? Whenever we are talking about unbiased means we can say we are not connecting this semiconductor with any electric source. Clear? So directly you can see this is just like at a room temperature. Clear? Now we know In p type of semiconductor, what is majority charge carrier? So we can say in p type of semiconductor we are having holes as majority charge carrier. In n type of semiconductor we are having electrons as majority charge carrier. Clear? So now which option is correct? Let us try to understand. Free electron in the n region attract them. So generally it is considered, sir, when we have majority charge carrier in n type of semiconductor, we have majority charge carrier hole. The hole is positive charge. So definitely we can say these electrons attract this hole, but this is wrong. Clear? Whenever we are talking about holes, concentration of hole in p region is very large compared to concentration of hole in n region. Now you can say, sir, in n region we have majority electrons, so how can you say about holes? I am saying a majority charge carrier in n type of semiconductor, that is electrons, but there is some hole is to be there and they are present in a minority form. Clear? So I can say maximum concentration of hole you will find in the p region, and there is a minority or we can say a very small concentration of holes you will find in n region. That's why we can say these holes actually transfer from p side to n side. Actually hole is what? We can say hole is a positive charge. We consider this as a positive charge, but actually what happened? In n type of semiconductor we have electrons, and electrons are having maximum concentration, or you can say majority charge carrier, and on the p side we have electrons but they are present in a minority form. Clear? It means we can say concentration of electron in n side is more compared to p. Clear? So all electron is actually jump to this, sum of electrons is jump to p side. Clear? So directly you can say whole concentration in p region is more as compared to n region. That's why we can say in an unbiased p-n junction hole diffuses from p region to n region. Clear to everyone? So this is all about this question. Now dear student, we are going to discuss question number 14.5. Clear? In this question it is given to you, when a forward bias is applied to a p-n junction, then what will happen? Clear? So first of all let us try to understand what is forward bias. So first of all I am saying to you, let's suppose this is p-n junction. Let's suppose this is p-n junction. I can say this is p, and let's suppose this is n. Clear? And let's suppose we are connecting it to a battery like this. It is connected to a battery, and we can say this is positive and this one is negative. Clear? So because when we can say this p-n junction is forward bias. P-n junction is forward bias when p side of this we can say p-n junction, it is connected to the positive of a battery, positive terminal of a battery, and n side is connected to negative terminal of a battery. Clear? So now we can say this is positive side, this is negative side, so we can say this is a forward bias. Clear? Actually you can also represent it in a symbol form like this. Clear? Now this one. Clear? So from here you can say this is plus minus. Clear? And now you can say this side is represented p and this one is n. Clear? So this is known as forward bias. Clear? Now let us try to understand, when a forward bias is applied to a p-n junction, what will happen? So initially whenever we are not connecting any current source, at that time you will find there is some we can say this is a depletion layer is to be formed between p-n junction. Clear? And we can say whenever we connect it in a forward bias, we can say, because in a p type of semiconductor majority charge carriers we have holes. Clear? And this side we have majority charge carriers electrons. Clear? So maximum holes they will try to move from this side to this side. Clear? Maximum hole try to move from this side to this side. Clear? So it means we can say what will happen, we can say this is actually thickness of this depletion layer, it decreases. Yes or no? Thickness of depletion layer decreases. Clear? So let us try to understand each option one by one. When a forward bias is applied, raises the potential barrier? No. Clear? Potential barrier means, let's suppose you can assume a battery, and in this battery we can say there is this is an imaginary battery, and we can say we are connecting positive this side, so you can say electric field is acting this side. Clear? So now we can say actually this is increases this depletion layer. Clear? So whenever we are saying we are applying we can say this is forward bias, So it actually raises the potential barrier? No, it actually reduces the potential barrier. It means option number A is wrong. Clear? Now, if I discuss about number B, it reduces the majority carrier current to 0. It reduces majority carrier current to 0. Majority carrier current. So no, actually majority carrier current actually increases by using forward bias. So this one is again wrong. Third part, lowers the potential barrier? Yes. Clear? So whenever we apply forward bias, at that time we can say thickness of depletion layer decreases, and we can say this potential barrier also decreases. So we can say option number C, this is correct. Clear? Now none of this is wrong, so I can say which option is correct? Option number C is correct. Clear to everyone? Now dear student, we are going to discuss question number 14.6. In this question it is given to you, in half wave rectifier what is output frequency if input frequency is 50 Hz. So do you know, actually let's suppose I am saying, let's suppose this is input wave. Clear? Let's suppose I am saying this is input wave. Clear? And frequency of this input wave, it is given to you 50 Hz. Clear? Now let's suppose I am saying this side we have an expression like this. Clear? And let's suppose I am connecting a diode like this. Clear? And we have a resistance like this. Clear? Now you can say in the first half cycle, because this is AC, in the first half cycle I can say this P end is at a higher potential and Q end is at a lower potential. Clear? So we can say at that time this diode it behaving just like a forward bias, and at that time if we are consider this diode as an ideal diode, we always find a waveform in our output circuit. Clear? But let's suppose in the second half means we can see whenever this cycle is changing, at the time this Q becomes plus. Clear? Or we can say at higher potential, and this P becomes negative, means at a lower potential. Clear? It means I can see now this is at higher potential, this one is at lower potential. At that time this diode becomes reverse bias, and whenever we have a reverse bias, we are considering this diode as an ideal diode. At that time you can say there is no output you will find. Clear? So this is known as half wave rectification. Clear? But one thing you should keep in mind, this one cycle is completed when this is going like this. Clear? But in an output form you can say this is one cycle, this one. So if initially we have total frequency 50 Hz. So after half wave rectification, you will find same frequency, this is 50 Hz. Clear? And actually what do you understand by rectifier? Rectifier is a device which is used to convert AC into DC. Clear? So now we can say in half wave rectification output frequency is 50 Hz. Clear? So now we are going to discuss same for the full wave rectifier. Clear? So now concentrate. Let's suppose I am saying this is input frequency we have, this is input frequency. Clear? And let's suppose I can say this is a coil. Clear? And now it is connected like this. Clear? Now let's suppose, because we are talking about full wave rectifier, so I am utilizing two diodes. Clear? So let's suppose this is diode number D1 and let's suppose this is diode D2. Clear? Now we are connecting these two diode like this. Clear? And actually I am using center tape rectifier. Clear? And actually this is having load resistance. Clear? Now listen very carefully. In the first half, whenever we are saying this is first half cycle, so for the first half cycle, let's suppose this is Q end, let's suppose this is P end. So for the first half cycle, this is at higher potential, this is at lower potential. Clear? At that time you can see this D2 diode. This D2 diode, it actually behaving just like a reverse bias. Yes or no? And we can say this D1, it actually behaving as a forward bias. Clear? So at that time definitely I can see some current will flow in this direction, and you can see, let's suppose I am taking this A and B. So in a load resistance, current is flowing from A to B side. Clear? And output form that you will get, this is output form in the first half cycle. Clear? What will happen for the second half? Clear? So for the second half you can see this side, it means we can say this point P, it becomes at higher potential and this becomes at lower potential. Clear? It means we can say now D2 diode, it behaving just like a forward bias and this is a act for a reverse bias. So now we can say again, if we talk about this is behaving just like an open circuit, this one is at closed circuit. Again you can say current is flowing from A to B side. Clear? It means now you will get the second waveform, it should be like this. Clear to everyone? It means I can say if initially frequency I am taking, this is 50 Hertz. Frequency is what? This is number of cycles completed in 1 second. So now you can say in this side every cycle is repeating from after this point A and B, after this point B. Clear? But now you can say in output form, this is output. In output form this cycle is repeating from A, C and B. So from A to C and again this cycle is repeating. It means we can say whenever we have one cycle related to this, at the same time 2 cycles is completed this side. Clear? So I can say frequency of output form, clear, this is equal to 100 Hertz. Clear to everyone? Clear? So in a half wave rectifier you will find same frequency 50 Hertz and in full wave rectifier you will find this is 100 Hertz. Clear? So this is all about this question. Clear everyone? Now student, we are going to discuss this question number 14.7. Clear? In this question it is given to you a PN photodiode. A PN photodiode is fabricated from a semiconductor with a band gap of 2.8 electron volt. Clear? So now I can say value of Eg. Value of Eg, it is given to you 2.8 electron volt. Clear? 2.8 electron volt it is given to you. Can it detect a wavelength of 6000 nanometer? Clear? So whenever we are talking about this one 6000 nanometer, so actually we know E is given by energy of a photon, this is given by h nu. Clear? We can also write it like this is Sc by lambda. Clear? Now we can actually find this value equal to 12,400 divided by lambda and I can put this lambda in angstrom. Clear? So from here you can see we can write like this. This is 12400 divided by what is value of lambda? Lambda value we are getting, this is 6000. Clear? 6000 nanometer. Nanometer means we can say this is 10 to the power minus 9. Clear? But actually we have to put this value in angstrom. So you can say we can divide with 10 and multiply it with 10. Clear? So from here we can write like this 12400 divided by, now we can say 123. Clear? 123 and multiplied with 0 and we can say this is 10 to the power minus 10. Clear? So now we can say this 10 to the power minus 10 meter, this is equal to 1 angstrom. So directly I can say I can write only 60,000. Clear? So now from here you can say 20 and 20 cancelled out. 1.24 divided by 6. Clear? 1.24 divided by 6 and this should be equal to 0.2. Clear? 0.2 and we can say we have this 0 and we can say this is 6. Clear? So 0.206 we can say electron volt, we can say that energy we are getting. Clear? Now if we want to find that it can detect, this semiconductor can detect this wavelength, no, because I can say this energy is less than, I can say energy gap. The energy E is less than energy gap. So from here we can say yes, this semiconductor, this photodiode cannot detect wavelength of 6000 nanometer. So photodiode cannot detect wavelength of 6000 nanometer. Clear to you? 6000 nanometer photodiode cannot detect wavelength of 6000 nanometer. Clear? So this is all about this question. Now we are going to discuss question number 14.8. Clear? In this question it is given to you the number of silicon atom per meter cube is 5 into 10 to the power 28. This is doped simultaneously with 5 into 10 to the power 22 atoms per meter cube of arsenic and 5 into 10 to the power 20 per meter cube of atoms of indium. Okay, calculate the number of electrons and holes, and it is given intrinsic charge carrier density, it is 1.5 into 10 to the power 6 per meter cube. This is number of number of atoms per meter cube, it is given to you. Now we have to also find this is N type or P type of semiconductor. Clear? So first of all, you can see it is given, we have arsenic. Arsenic means we can say this is pentavalent. Pentavalent means we can say this is donor. So I can say Nd. I am saying Nd value I am taking, this is 5 into 10 to the power 22, this is atoms per meter cube. Clear? Now we can also say, we can write this is indium. Clear? Indium means we can see this is acceptor, and this value is given 5 into 10 to the power 20 atoms per meter cube. Clear? And value of Ni, it is given to you, this should be equal to 1.5 into 10 to the power 16 atoms per meter cube. Clear? Now if we talking about, let's suppose we have total number of electrons and holes, this is represented by Ne and Nh. Clear? And this is our objective also. So if we want that this crystal lattice, it should be electrically neutral. So at that time we can see, we can write like this, Ne minus Nh, it should be equal to Nd minus Na. Yes or no? Means we can say the difference in the donor and the acceptor ions, it should be same as the number of electrons and number of holes. So now we can say, let's suppose this is equation number 1. Clear? Now actually we know one more relation, Ni square, this should be equal to Ne multiply Nh, and let's suppose this is equation number 2. Clear? So from here we can say, we can write like this, Ne plus Nh, this is whole square. Clear? How can we find it? We can see this, we can write like this, Ne minus Nh, this is whole square plus 4 times Ne Nh. Clear? Ne Nh. So now we can say Ne plus Nh, this is whole square, equal to, what is value of Ne and Nh? This is equal to, we can see Nd minus Na whole square plus 4 times. Now we can see this is equal to Ni square. Clear? So now we can see, we can write like this, Ne plus Nh, this should be equal to under root of Nd minus Na whole square plus 4 times Ni square. This is, let's suppose, equation number 2. Clear? Now you can see, let's suppose this is equation number 3. Clear? Now if we add equation number 1 and 3. Clear? So if I am adding 1 and 3, so we can see this is 1 plus 3. So whenever we are doing 1 plus 3, you can see Nh and Nh, this is cancelled out, and we can write this is equal to twice of Ne, and it should be equal to, now we can say Nd minus Na. So directly you can say this is Nd minus Na plus under root of Nd minus Na whole square plus 4 times Ni square. Nd minus Na whole square plus 4 times Ni square. Clear? So from here you can say what is value of Ne, this should be equal to 1 by 2 Nd minus Na. Clear? Plus under root of Nd minus Na whole square plus 4 times Ni square. Clear? Now you can place all the values. So we can say any value, we know 1 by 2. Now what is value of capital Nd? Capital Nd is given, yes, 5 into 10 to the power 22. So 5 into 10 to the power 22 minus, what about Na? 5 into 10 to the power 5 into 10 to the power 20. Clear? Plus under root of. Clear? Now you can place all values. So 5 into 10 to the power 22 minus 5 into 10 to the power 20 whole square plus 4 times, what is value of Ni? Ni is given 1.5 into 10 to the power 16. So we can see 1.5 into 1.5 into 10 to the power 32. Clear? So this is divided by 2. Clear? Now we have to solve it. So definitely we can solve it. It's very easy calculation. not an easy calculation, but we can make it easy. If we are taking 10 to the power 20 common, we can say we have 500 minus, so 495 into 10 to the power 20 plus. Now you can say this is what value? I can say this is 495 into 10 to the power 20. Yes, 495 into 495 into 10 to the power 40 plus. Clear? Now we can say this value you can multiply 4 into 2.25 into 10 to the power 32. Definitely you need calculator to do some type of calculation. Directly I am saying to you, approximately you will get this value any 4.95. Clear? 4.95 into 10 to the power 22, and we can say this is atoms, number of electrons per meter cube. Clear? We can say this is number of electrons per meter cube. Clear? Similarly, you can find value of we can say NH. How can we find? So now you know value of Ne minus NH, you know Nd minus Na. Clear? And this is equal to Nd. Nd you know this one and this one. So from here you can say, can we write like this, 495 into 10 to the power 20? Yes or no? So can we find value of NH? Yes. So directly I can say I am writing here Ne minus NH, this should be equal to 495 into 10 to the power 20. Now what is value of Ne we are getting? This is 495 into 10 to the power 20, near about. Yes or no? Just a minute. Clear? You are getting this value Ne, this one. Clear? And actually you can find this value. Just a minute. You can find value of NH by very simple we can say calculation. This value you can take NENH, this should be equal to Ni square. So from here you can say NH, Ni we know this is 1.5 Ni, 1.5 into 10 to the power 16. Clear? This is whole square and divided by what is value of Ne, this is equal to 4.95 into 10 to the power 22. Clear? Now if you solve it, you will find this answer near about 4.5 into 10 to the power 9 per meter cube. Clear? So now if you compare, you can say we can say number of electrons, you can say number of electrons are greater than number of holes. Definitely it means we can say number of electrons are majority charge carrier and number of holes are minority charge carrier. Clear? It means I can say this is which type of conductor. Directly we can say this is N type of semiconductor. N type of semiconductor. Clear? This is what? This is N type of semiconductor. Clear to everyone? So this is all about this question. So student, now we are going to discuss question number 14.9. Clear? In this question it is given to you, in an intrinsic semiconductor the energy gap is 1.2 electron volt. Its Hall mobility is much smaller than the electron mobility and it is independent of temperature. Fine. What is the ratio between conductivity at 600 Kelvin and that at 300 Kelvin? Okay. Assume that the temperature dependence of intrinsic carrier concentration is given by Ni equal to N0 exponential e minus of Eg divided by 2 kBT. Clear? Where N0 is a constant. Clear? So now let us try to understand this question, and first of all understand what is our objective. Our objective in this question is to find ratio of conductivity. Ratio of conductivity at 600 Kelvin and at 300 Kelvin. Now dear student, do you know what is the relation between conductivity and mobility? Yes. So actually you know, definitely we can say sigma, this is equal to N, E and mu. Clear? In generalized term I am writing this mu is the total mobility and sigma is conductivity. Clear? But actually it is given we have intrinsic semiconductor. Clear? So we can write like this, for intrinsic semiconductor. Just a minute. Now we can say this is for intrinsic semiconductor. We can say this should be equal to Ni is equal to Nh divide is equal to number of electrons. Means I can say charge carrier concentration of intrinsic semiconductor, this is equal to total number of electrons, or we can say hole concentration, and this is electron concentration. Clear? And we also know it is given in this question that the mobility of electron, it is much higher compared to mobility of hole. Clear? Okay. Now we know relation between conductivity and mobility, it is given by sigma. This should be equal to n, we can see this is n E. Clear? We can say it means this is the Ne. Clear? Ne means this one. Ne, we can say charge of electron, and we can say this is mobility of electron plus. Clear? Now I can say this is related to NH, this is E, and we can say this is mu H. Clear? So now we can say, because we have intrinsic semiconductor, so directly we can say NH and Ne, NH and Ne both are equal to Ni. Clear? So from here you can take E and I common. From here we can say this is mu E plus mu H. Clear? Sigma equal to E times of Ni mu E plus mu H. Clear? Now actually you know this mu E is very greater than compared to mu H, so you can ignore this mu H compared to mu E. Clear? So now I can say we can write like this, sigma, it is given by Ni, this is E, and we can say this is mu E. Clear? And let's suppose now I am saying this is equation number 1. Clear? This is equation number 1. So now you can say we can also write like this, sigma equal to Ni, this is E, and we can say this is mu E. Clear? Now how can we write this expression? Clear? So we can say Ni, sigma, Ni we can say it is given in this question, Ni equal to N naught exponential power minus times of Eg by 2 kb and multiplied with T. So we can say Ni, this is E, and this one is mu E. Now we can say value of Ni, this is equal to N naught. Clear? So N naught E, and we can say this is mu E. Clear? Multiply. Now this is exponential power minus Eg divided by 2 times kb multiply T. Clear to everyone? So from here you can say, let's suppose I am assuming this N naught E mu E, this should be equal to sigma naught. Clear? So I am taking this as a constant, so we can say this is sigma naught E to the power minus Eg divided by twice of kb T. Clear? Now if I write this value at 600 Kelvin, clear, as this is given in this question, we have to find ratio of thermal we have to find the ratio of conductivity at temperature 600 Kelvin and at 300 Kelvin. Clear? So now we can say this is given by sigma naught E to the power minus Eg divided by 2 kb and multiply, we can say this is 600. Clear to you? Similarly you can write conductivity at 300 Kelvin also, this is equal to sigma naught. Clear? E to the power, now we can say minus times of Eg 2 kb and multiply, this is 300. Clear to everyone? So now if you divide both, let's suppose this is equation number 2 and let's suppose this is 3. Clear? So if I divide 2 and 3, we can say sigma at 600 Kelvin. Clear? And we can say sigma at 300 Kelvin, this is equal to, clear, sigma naught and sigma naught, this one is cancelled out, and we can say e to the power minus Eg, we can say this is 1200, and we can say this is kb, divide by, clear, e to the power minus, we can say Eg, divide by, we can say this is 600 and this one is kb. Clear? So now if you solve it, you can say we can write like this, this is e to the power minus Eg divided by kb, I am taking common. Clear? I am taking this one is common, so because this is going, this one becomes positive, but we can write this is 1 by 12 minus 1 by 600. Clear to everyone? Yes. So now if you take LCM, you can say this is Eg divided by, now we can say this is Eg divided by, this is kb, and if you are taking LCM, this is 1200, 1 minus 2. Clear? So now we can put all values, e to the power minus Eg. Eg is given to you in this question, yes, 1.2 electron volt. So can we convert this into joule? Yes, 1.2 into 1.6 into 10 to the power minus 19, clear, divide by, clear. Now we can say this value we have multiply minus 1 by 1200, clear. And what is value of kb? kb is Boltzmann constant, so we can say this value is 1.38 into 10 to the power minus 23, this is joule per Kelvin, clear. So now if you solve it, you can say minus minus becomes plus, clear, and if you solve it, clear, you will find this value near about e to the power 11.6, clear. If you solve it, you will find it, clear. So directly you can say, let's suppose if you multiply 16 multiply 2, 32, clear, we have 3, so 192 and it is divided by this one. So if you calculate, you will find this is near about 11.6, clear. Exponential power 11.6. Now you can say, sir, how can we calculate? Definitely you cannot calculate it without calculator, clear. So you can take some approximation, but it definitely at initial level it is very difficult to take approximation also for exponential. So what we can do, you can do one thing directly, you can find some approximation, clear, and directly I am telling you this answer, and this value you are getting 1 into 10 to the power, we can say 5, clear. So directly from here you can see we are getting this ratio. What? We are getting this ratio sigma, we can say conductivity at 600 Kelvin and 300 Kelvin, this is near about 10 to the power 5. It means I can say as I am increasing temperature, conductivity of a semiconductor or conductivity of a material that increases, clear. So now I can say for semiconductor, if you are increasing temperature, definitely their conductivity increases, clear. So this is all about this question. Now student, we are going to discuss this question, and this is a question number 14.10, clear. In this question it is given to you, in a PN junction diode, the current can be expressed as I equal to I naught exponential EV divided by twice KBT minus 1, where I naught is given to you, this is reverse saturation current, V is a voltage across the diode, and it is positive for we can say positive for forward bias and negative for we can say reverse bias, fine. Now kb is a Boltzmann constant, and its value is given to you in electron volt per Kelvin, clear, and this value is 8.6 into 10 to the power minus 5, clear. What is value of capital T? Capital T is given to you, this is absolute temperature, clear. Now it is also given, if for a given diode I naught equal to 5 into 10 to the power minus 12 ampere and temperature is given to you 300 Kelvin, then we have to find that answer of these four parts A, B, C and D. So first of all we are going to discuss part number A, clear. So now concentrate. Now in this question it is given to you, in a PN junction diode, the current I can be expressed as I equal to I naught exponential EV divided by twice KBT minus 1, clear. So it means first I am writing this expression again. So this is equal to I naught, clear, I naught exponential power, and now I can say EV divided by twice KBT, minus 1, clear, EV divided by twice KBT minus 1. So this is an expression of current, clear, where I naught is what? We can say I naught is known as reverse saturation current, and V is the voltage across diode, and it is positive for forward bias and negative for reverse bias, clear. So first of all we are going to discuss part number A, clear. So part number A. In part number A, it is given to you what will be forward current at forward voltage of 0.6 volt, clear. So first of all we are writing this value 0.6 volt, clear. So what is value of current at 0.6 volt? So for that one, first I am calculating this value EV divided by twice KBT, clear. Now E is the charge of an electron, 1.6 into 10 to the power minus 19, clear, multiply what is V? V is given to you, this is 0.6 divided by, clear, divided by this is 2 multiply what is KB? KB we can say the value is given to you 8.6 into 10 to the power minus 5. So 8.6 into 10 to the power minus 5, but this value is given to you in electron volt per Kelvin, clear. So we can multiply it with 1.6 into 10 to the power minus 19. because 1 electron volt is equal to 1.6 into 10 to the power minus 19 joule. Clear? And what about temperature? Temperature is given to you 300 Kelvin. Clear? This temperature is given 300 Kelvin. Clear? Now we have to solve this expression. So you can say 1.6 into 0.6 into 10 to the power minus 19 divided by. Clear? Now we can say 2 into 8.6 into 1.6 into 10 to the power minus 24 into 300. Clear? So now if you say, we can say this is equal to 8. Clear? And we can say 8 into 6 into 10 to the power minus 19 divide by 8.6 into 16 into 10 to the power minus 24 into 300. Clear? Now if you solve it, you will find this expression. This expression is equal to near about, I am directly telling you near about answer is 23.26. 23.26. Clear? So can we find value of current at this voltage 0.6 volt? Yes. Now I equal to I naught. I can say this is I naught exponential power. We can say this is 23.26 minus 1. Clear? Can we write like this? Yes or no? Exponential power minus 1? No, actually this is exponential and we can say this is power minus 1. Clear? So now we can say I equal to I naught exponential 23.26 minus 1. Clear? So now you can also write it like this, I equal to I naught E exponential power. This is exponential power. Clear? And we can say this is 22.26. Now what is value of I naught? I naught is given to you, this is saturation current. Clear? And saturation current is given 5 into 10 to the power minus 12 ampere. Clear? So 5 into 10 to the power minus 12 multiply. Now this is what we can say e to the power 22.26. Clear? Now if you solve it, means if you find value of e to the power 22.26, definitely you have to find it by with the help of calculator, or either it will be given to you in the question also. Clear? That what is value of e to the power 22.26. Clear? And it is multiplied with this one. Clear? So whenever you solve it, clear, you will find this value 0.0232 ampere. Clear? Whenever you find this expression, your answer will come out to be nearby this one. Clear? Now so we can say this is current flowing in a forward bias condition when we have voltage 0.6 volt. Clear? So this is answer of part number A. Clear? What will be the forward current? This is value of forward current. Clear? Now we are going to discuss part number B. What is part number B? What will be the increase in the current? What will be the increase in current if the voltage across diode is increased to 0.7 volt? Clear? And in part number B, it is given to you when we have 0.7 volt. 0.7 volt. Clear? Again we find the value of EV divided by KB multiply T. Clear? EV divided by KB multiply T. So what is value of E? We can say this is 1.6 into 10 to the power minus 19. Clear? And okay, I am writing it as a here. I am not writing here, I am writing below something. Clear? So because calculation is lengthy, so that's why I am writing here. I can say now value of EV divided by KB multiply T. Clear? Value of E, we can say 1.6 into 10 to the power minus 19. What about value of V? Value of V given 0.7 volt. Clear? And divided by what is value of KB? KB you can say 8.6 into 10 to the power minus 5 electron volt per Kelvin. We can convert it into joule also. Clear? So 8.6 into 10 to the power minus 5 multiply 1.6 into 10 to the power minus 19. Clear? And at the same temperature means this is 300. Clear? So now dear student, if you solve it, clear, you will find this value. This is EV by KBT. Clear? This value you will find, this is 27.13. Clear? So now I can write expression of I is given by I naught. Clear? Now we can say this is exponential power. Clear? 27.13 minus 1. Clear? So from here you can see, if we put value of I naught 5 into 10 to the power minus 12, and we can say e to the power 26.13. So if you find complete value of this expression, clear, you will find this value 1.257 ampere. Clear? 1.257 0.27 ampere. Clear? Definitely you need calculator to solve this problem. So 1.257 ampere. Clear? Now what is question? Question number B. Clear? Question number B is given to you. What will be increase in current if the voltage increase from 0.7 volt? Clear? So I can say what is change in current, delta I, it should be given by 1.257 ampere current. This is at 0.7 volt, and we can say this is 0.0232 ampere. This is at 0.6 volt. Clear? So now you can say if you write it 1.237 ampere. Clear? So this delta I value you are getting this one. Clear? Now in the next question it is asking to you what is the dynamic resistance. Clear? So my dear student, what do you understand by dynamic resistance? Clear? Dynamic resistance means we can say delta R, this is given by delta V divided by delta I. Clear? Now what is change in voltage? Clear? Change in voltage is given by 0.7 minus 0.6 divided by, clear, what is change in current? Change in current, you can see we are having this change in current 1.237 ampere. Clear? So 1.237 ampere. Clear? So from here we can say this is 0.1 and divide by 1.237. Clear? So now if you solve it, you will find this value near about 0.081 ohm. Clear? So we can say this is value of dynamic resistance. Why I am saying this is dynamic resistance? Because in a semiconductor Ohm's law is not followed, because potential difference and current, it will not in a proportional relationship. Clear? So directly we can say that's why we are finding dynamic resistance. Clear? Now we have part number D, and in part number D it is given to you what will be the current, if the reverse bias voltage changes from 1 volt to 2 volt. Clear? So dear student, if you know characteristics, if I draw here a graph between current and voltage, and if we are talking about reverse, we can say reverse, we have a forward bias and reverse bias. So if you draw for the reverse bias, you will find this curve something like this. It means we can say for the variation of some voltage you are getting constant saturation current, constant reverse saturation current. It means we can say whenever we are increasing this potential. Clear? Whenever we are increasing this potential from 1 volt to 2 volt. Clear? At the time you are getting constant reverse saturation current, and value of that I naught, it will remain same, 5 into 10 to the power minus 12 ampere. Clear? And always keep in mind the magnitude of this reverse saturation current, this is very small. Clear? So this is all about this question. Now student, we are going to discuss question number 14.11. Clear? And in this question it is given to you are given the two circuit as shown in figure. Definitely this is circuit number A, and we have one more circuit, this is circuit number B. Clear? So these two circuits are in only one question, 14.11. Clear? So now in this question it is given, we have to show that this circuit A act as an OR gate while the circuit B act as a AND gate. Clear? So this circuit is actually given to you, and directly from observation you can see actually you can observe some important result from this side. Actually you can see this is the symbol, it is the symbol for OR. Clear? And let's suppose if we are drawing like this, now this becomes NOR. Clear? And we can say this is actually NOT gate. Yes or no? This is NOT gate. So it means NOR and NOT, I can say this becomes OR. Clear? So we have to actually show that this act as a OR gate. Clear? So the best way to solve such type of logic gates, and that is what we can say, you have to take input A and B, you have to put value 0, 0, 0, 1, 1, 0 and 1, 1, and let's see whatever output we are getting. Clear? So for that one I am drawing here a truth table. So I am saying, let's suppose we have two inputs A and B. Clear? So from A and B we are getting this is Y dash. Clear? And we can see this Y dash is actually what? First I am getting this is A plus B, and this should be equal to Y, because this is not a OR gate, this is NOR gate. Clear? So I will find this is Y bar. Clear? So with this Y bar, we can say this is equal to y dash, clear? Or you can also write it like this. If you are getting confused, directly you can say you are getting this y equal to a plus b, clear? And you can say this y dash you are getting a plus b, and this is not, clear? And after that we have this is not gate, so I can say this is y dash not, or we can say this is equal to, we can say a plus b, not we already have, now we are having double not, clear? So now let us try to put some inputs and let us try to find what final output we are getting, clear? Actually this value is given to you, this is equal to y, clear? Now listen carefully. Now first of all I am placing this value of a 0, clear? And this is also 0. Listen carefully. Whenever I am placing this value 0, this one is also 0. Now we can say 0 plus 0, clear? This input is equal to 0, I can say this is 0, but here we have NOT gate. So what is, we can say if this is 0, this is becomes 1, because in digital algebra, we can say Boolean algebra, we have only two digits, 0 and 1. 0 represent off switch and 1 represent on switch. So let's suppose this side we have off switch, this one is again off. So final we can say this is, we are getting 0, but this is 1, clear? Whenever we have 1, we have NOT gate. NOT gate always convert opposite signal, means we can say, let's suppose we have 1, clear? So here we get 0. If we have 0, we get 1, clear? So this is 1, I can say this one is 0. Clear to everyone? Yes. Now you can say, now we can say, let's suppose I am saying this is 0 and this is 1, clear? So now I am placing this input instead of this 0, now this is 1, clear? So 0 plus 1, we have 1, clear? And we can say this is equal to 1. So now we can say not of this one, we have this is 0, clear? And when we have 0, again we have not, this is we are getting 1, clear? So now let's suppose if my input is 1 comma 0, clear? Again you can say, we can write like this 1 comma 0, clear? This is 1 comma 0. So now we can say we are getting this output, this is 1, clear? If we are taking not, this one is 0, clear? And if this is 0, we can say this is 1, clear? And now if we take one more input, let's suppose we have this 1 and this is 1, clear? So now I am taking two input, this is 1, clear? This is 1 and this one is also 1, clear? So 1 plus 1, this is equal to 1, not 2, clear? So 1 plus 1, this is equal to 1, but we are taking not, so that's why this is 0, and again we are taking not, so this is 1, clear? Now concentrate on the truth table, clear? This is known as truth table. Truth table. Now consider here, what is your input? Our input in this case is only A and B. And what is your output? Output we have, this is Y, clear? Now you can say if we have input 0 0, we are getting output 0. If we have input 0 1, we are getting this is 1, clear? If we have 1 0, we are getting again 1, clear? And if we have two input 1 and 1, we are getting 1. It means this is truth table related to OR gate, clear? So I can say this figure number A, it is showing a logic gates corresponding to, we can say this is OR gate, clear? This is showing logic gate corresponding to OR gate, clear? OR gate. And we can say this is actually final output, we can say if we write in a algebraic expression, we can say it is represented by A or B, like this. Yes or no? This is known as A or B. So y equal to A or B. We never say y equal to A plus B. No. In logic gate concept, you always find this is y A or B. Clear? So now we can say this is all about part number A. Clear? Now we are going to discuss same in the question number 14.11. This is figure number B. Again we have two inputs A and B, and let us try to find what is output we are getting at Y. Clear? Again I will draw two table. So first I am saying we have input, this is A. Clear? Now listen very carefully. I am taking one more input, this is B. Now listen, because we connected NOT gate, clear? So first we will get this is A dash, clear? Or we can say this is B naught, clear? A naught and B naught we are getting this side, this is A naught and this one is B naught. clear. Now you can see as a input we have A naught and B naught, and we are getting this is NOR gate. So NOR gate means we can say this is A plus B, clear. After that you are getting this A naught or not B, and this is total not, clear, and this should be equal to Y, clear. Now we can put all the values and let's see what truth table we are getting, clear. So first I am placing this value 0, this one is 0, means 0 input 0 input, we are getting this is 1 and 1, clear. 1 plus 1 we have 1, clear. So this is 1, and here we are getting this is 0, clear. Now let's put another input, clear. Another input is given A value we are taking this is 0, clear, we are taking this is 1. So what is not of A, we can say this is 1, and what is not of B, this one is 0, clear. Now 1 plus 0 we have this is 1, clear. Now what is not of this one, we can say this is 0, yes or no. So now from here you can say, let's suppose I am taking this is 1 and let's suppose this is 0. Again what is not of this one, this is 0, clear, and what is not of this B, this is 1. 0 plus 1 we are getting this is 1, clear, and what is not of this expression, this is again 0, clear, this is again 0, clear. Now like this. Now let's suppose I am taking two inputs 1 and 1, clear, I am placing 1 and 1, so we have two not, again we can say this is 0 and 0, clear. 0 plus 0 we are getting this is 0, clear, and we are taking not, so this is equal to 1, clear. So from here you can see what is actual input and what is actual output. So actual input we can say this is 0 0 we are getting 0, clear. We can say 0 1 we are getting this is 0, clear. 1 0 we are getting again 0, and 1 1 we are getting 1. It means this is truth table related to AND gate, clear, this is related to AND gate. Okay, actually you can observe a very important result from part number A and part number B, clear. This is part number A and B. Actually what you are doing, what we are doing, you are understanding. Actually we are getting basic gates from universal gates, clear. Actually NOR gate and NAND gate, it is NOR gate and NAND gate, actually it is considered as a universal gate, clear. So in this question actually by using NOR gate we are getting first OR gate, and by using NOR gate we are getting AND gate, clear. Similarly we can also find NOT gate by using NOR gate, clear. So actually by using this NOR gate, because in this question we have only NOR gate, by using NOR gate we can find OR gate, AND gate and NOT gate, all the basic gates we can find from here, clear. So this is all about this question. Now dear student, we are going to discuss this question number 14.12, clear. And in this question a logic gate is provided to you. Actually you can see we have this is NAND gate, clear, and actually we are connecting both the inputs of this gate, clear. Now we have to find that what is exact logic operation that is carried by this circuit, clear. So now concentrate. So first of all we can say, let's suppose we are taking this is input A, so I am saying this is input A, and let's suppose we have B and B is also equal to A, yes or no, because both are connected with the same signal, clear. So I can say I am taking this is A, clear, and I am saying this is B, clear to everyone. Now listen, because it is given to you AND gate, NAND gate, so I can say AND means we can say A and B like this, and after that we are getting this is A and B and this is not, yes or no. And after that actually this is what, this is equal to Y, clear. Now you can place all values. So first I am writing A 0, so whenever I am saying A 0 it means B is automatically 0, yes, so this is 0. A and B we are getting 0, and this is not, we are getting 1, clear. Now similarly, now let's suppose your input is 1, clear, automatically B also 1. A and B is also 1, and if you are getting not means we can say this is 0, clear. So now we have only two probability, we can say actually two values you can place here. Why? Because if you are writing 0 then both becomes 0, if you are saying we have 1 then both becomes 1, clear. So directly you can say actually what is exact logic operation is carried by this circuit. Listen carefully. If we are having off, or we can say if we are taking input 0, we have output 1. Clear? If we are taking input 1, then we are getting output 0. It means what we can say? We can say that this is just behaving like a NOT switch. Yes or no? If you are saying as an input 0, you are getting 1. If you are giving input as 1, you are getting 0. Clear? So I can say exact logic operation, it is carried by this is NOT gate. Clear? We can say exact logic operation it is carried by this is NOT gate, NOT. Clear? So I can say this is all about this question. Now student, we are going to discuss this question number 14.13. Clear? And in this question it is given to you are given two circuit as shown in figure, okay, which consist of NAND gates. This is one circuit and this one is another circuit. Clear? So actually two logic gates, basically two logic gates are given to you, and you can say basically two circuits are given to you by using logic gates. Clear? So this is first circuit using NAND gate and this is another circuit using NAND gate. Clear? Now we have to identify the logic operation that is carried by these two circuits. Clear? So directly if you have a knowledge, or you can say if you have exact knowledge of logic gate, you can see because this is NAND gate, we can say this is NAND gate, and NAND gate is connected with the NOT gate, because recently we have already seen that this is behaving just like a NOT gate. So we can say this is NAND gate, this is NOT gate, so automatically you can say we are getting here AND gate. Clear? So again first we are drawing a truth table and let us try to understand what we are getting. Clear? So as an input first we have A, I can say this is B, because this is first AND gate, so I can say A and B. Clear? Because this is NOT gate, so I can say this is A and B NOT, and we can say let's suppose this is Y dash, so I am saying this is Y dash. Clear? Now you can say at this side we are getting same input. Clear? Same input means we can see, let's suppose we can say this Y dash is equal to A and we can say Y dash is equal to B. Clear? And after that we are getting NAND gate. NAND gate means we can say we are taking this is A and B and we can say this one is this one. Clear to you? And this is equal to we can say Y. Yes or no? And if you are getting confused, clear, you can say let's suppose we are taking this is A dash, B dash, so this is A and B dash and this is NOT gate. Clear? So now we can place all values and we can find our answer. Now listen very carefully. First I am taking as a input 0 0. So this is 0 0. 0 and 0 we are getting 0. Clear? This is NOT, so we are getting 1. Clear? So when we have Y dash 1, we can say this is 1, this is also 1. Clear? This is A dash and I can say this is B dash. Because both are connected with Y dash, it means both are having same input. So 1 and 1. So we can say this is 1, but this is not, so we can say this one is 0. Clear? Now if I again draw truth table, let's suppose I am saying this is 0 and let's suppose this is 1. Clear? This is 0 and this is 1. So 0 and 1 we are getting 0, so this is 0. Clear? Now we are getting NOT, it means this is equal to 1. Yes or no? Now I can say again as an input we are getting 1 1. Clear? So 1 and 1 we are getting 1 and NOT, then we can say this is 0. Clear? Now if we are taking again input 1 and 0, we can say A and B we are getting this is 0, this is 1. Clear? So I can say this is 1 and this is also 1. Clear? And 1 and 1 we are getting 1, and if we are taking NOT, this becomes 0. Clear? Then now let's suppose I am saying we have input 1 and 1, so we are getting this is 1 and 1, this is we can say 1. Clear? This is NOT, so we are getting 0. Again we have both input, this is 0, so 0 and 0, this is 0 but we are getting NOT, so this is 1. Clear? Now concentrate on the input and output part. Clear? So in the input we have 0 and 0. Clear? And we are getting output, this is 0. Clear? 0 1 we are getting 0. Clear? 1 0. Clear? We are getting this is 0. Clear? We have 1 and 1. and we are getting this is 1. It means this is just like a truth table of AND gate. Clear? So I can say logic operation, actually this complete circuit, it is behaving like a AND gate. Clear to everyone? And I already told you this is NAND gate, we are connecting a NOT gate, so negative and negative, we can say this become positive, so we can say we are getting AND gate. Clear to everyone? So this is only one part of this question. Now we are going to discuss part number B. Clear? And this is again related to 14.13. Clear? Now you can say we have this is NAND gate, and we can say two NOT gate are connected in parallel. Definitely I can say this becomes OR gate. Clear? This is OR gate. Clear? So again first we draw truth table. So I am saying this is A and B, we have two inputs. Clear? So now we can say if we have this is A, now directly you know this is A naught and this is B naught. Clear? Now no need to solve this one. Clear? Directly we can say A and A naught, B and B naught. So we can say this is A naught and B naught. Now we are saying this A naught and B naught is going as an input. So now we can say A naught and B naught. Clear? And after that we are taking, because this is NAND gate, so it will be like this, and this should be equal to Y. Clear? So yes. Now from here we can say, let's suppose we are saying input is 0 and 0. Clear? 0 and 0. So not of 0 we have 1, this one is again 1, 1 and 1 we have 1, and we are taking 1 and then we are taking not, so this become 0. Clear? Now let's suppose as a input I am taking this is 0 and this one is 1. Clear? This one is 0 and this one is 1. So now we can say not of 0 we are taking this is 1. Clear? And not of B we are taking this is 0. Clear? So we can say 1 and we can say A and B we are getting this is 0. Clear? And we can say if we are taking not, this becomes 1. Clear? Now listen carefully. Now you can say let's suppose I am taking this is 1 and 0. Clear? For that one you can say here we have input, this is 0, we can say this is 1 and 0, we are getting this is 0, and now we are getting this is 1. Clear? Next one, last one. Clear? Now you can say let's suppose I am taking 1 and 1 as a input. Clear? This is 1 and this is 1, so we can say not of 1, this is 0, I can say this is again 0, 0 and 0, we are getting 0 and we are getting not, so this is 1. Clear? Now if you concentrate on input and output part. Clear? In the input part we are taking 0 and 0, we are getting in the output 0. Clear? 0 and 1 we are getting output as 1. Clear? 1 and 0 we are getting again 1. Clear? And 1 and 1 we are getting 1. Clear? So this is truth table related to OR gate. Clear? So that's why I already told you we are connecting two NOT gate in the two parallel NOT gate with the NAND gate. So definitely we will get this is OR gate. Clear? Yes or no? So that's why I am saying to you NOR gate and NAND gate both are considered as a universal gates. Clear? Actually we can make any basic gate by using these gates. Clear? So I can say this is all about this question. Now student, we are going to discuss question number 14.14. Clear? And in this question we have to write the truth table for circuit given in figure below consists of NOR gates, and we have to identify the logic operation and OR gate, AND gate and NOT gate which the circuit is performing. Clear? So if you have a knowledge of logic gate, directly you can say this is NOR gate and this is NOR gate, and we are actually connecting with NOT gate. Yes or no? Because if we connect both ends, both inputs of this NOR gate, it becomes NOT gate. So NOR plus NOT, this becomes OR. Clear? So definitely we will get OR gate, but let us try to understand by using truth table. I am saying this is A and B. Clear? A and B. Definitely we will get first A plus B, and we can see this is what we can say NOR. Clear? And after that we are getting, let's suppose this is Y dash. Clear? So I can say this is A dash, let's suppose this is A dash and B dash. So Y dash is equal to A dash. Clear? And Y dash it is equal to B dash. Now we are getting again we can say NOR. So NOR means we can say A dash plus A dash or B dash, and this is NOR. yes, and this is equal to, we can say, y. Clear? Now we can place all values of inputs, and definitely we will get here 4 possibilities. So now we are going to discuss first one by one. Clear? So let's suppose I am saying input is 0 and 0. 0 or 0, we have 0, but this is 1. Clear? I can say this input is 1, this one is also 1. 1 or 1, this is 1, and we are getting this one is 0. Clear? Now if I am saying if input is 0 comma 1, so I can say this is 0 and 1. Clear? 0 and 1, we have 0 or 1, this is 1, but this is not, so I can say 0, this one is 0, this one is 0. Clear? Now 0 or 0, we are having this is 0, but this is not, so we have this is 1. Yes. Now let's suppose we have input as 1 and this is 0. Clear? I can say this is 1 and 0, we have this is 1, but understand it, this is not. Clear? So we are getting this is 0. Clear? When this is 0, this is 0, this one is 0. Clear? 0 or 0, we have 0 and this is 1. Clear to everyone? Yes. Now we can see, let's suppose I am saying to you this is 1 and this is 1. Clear? So 1 and 1, we are getting this is 1 and we have not, so this is 0. Again we can say input we have 0 and we will get this is 1. Now if you concentrate input and only output, clear? We can say your input is 0 and 0, you are getting this is 0. 0 and 1, you are getting 1. 1 and 0, you are getting 1. 1 and 1, you are getting 1. It means this is truth table of OR gate. Clear? So definitely the logic operation, this is carried by this circuit, it is OR gate. Yes or no? OR gate. Clear to everyone? Yes. Clear? Yes. So I can say this is all about this question. Now student, we are going to discuss question number 14.15. In this question we have two logic diagrams, two circuit diagram, you can say this is one and this is another one. Clear? Now we can say we have to write truth table for the circuit given in figure consisting of NOR gates only. Okay. Identify the logic operation performed by two circuits. Now directly you can say this is what? NOR gate. Clear? And NOR gate input are connected to each other, so definitely this becomes NOT gate. Clear? Similarly you can see this is NOR gate. Clear? Now we can say this is NOT and NOT. When two nodes are connected in parallel, clear, and we have this is NOR gate, this becomes AND gate. Clear? So definitely let us try to understand how this will be performed. Clear? So now I can say let's suppose I am saying first input we have A, let's suppose this side we have A, and let's suppose we are saying B, and definitely this B should be equal to A. Clear? So this is B. Because this is NOR gate, we can say first I am writing A or B and this is NOR. Clear? So, and actually this is equal to Y. Clear? Now what are input we are taking? First I am saying this is 0. When this is 0, I can say this is also 0. Clear? So 0 or 0. Clear? We are getting this is 1. Clear? Now what I am saying 0 1. Clear? 0 and 0, or we can see what I am saying to you. Clear? When A equal to 0, we have B 0. Clear? Now let's suppose I am taking A equal to 1. Clear? A equal to 1. At the same time you can say B is also equal to 1. So A or B, this is equal to 1, but we are getting 0. Clear? So directly you can say we have input 0, we are getting output 1. We have input 1, we are getting output 0. Definitely this is behaving just like a NOT gate. Clear everyone? Yes. Now we are going to discuss part number B of this question, and in this question again first let us try to perform truth table. This is A, and we can say when this is A, this is NOT gate. We have already seen recently in this one. Clear? This is represented as a NOT gate. So directly I am saying this is A, and we can say first I am writing input. So A and B, we have two inputs. Clear? After that you are getting this A dash and A naught, and we can say B naught. Clear? And because this is NOR gate, clear, NOR gate means we can say A, not A, or not B, and this is not. Clear? And this is our output, this is Y. Clear? So Now from here you can see we can write like this. Let's suppose we have this is 0 and 0. So definitely this is 1 and 1 because this is not clear. Now we can say 1 or 1. This is 1 and we have this is not, so this is 0. Clear? Now from here you can say let's suppose this is 0 and this is 1. Clear? So we can say this is 1 and this one is 0. Clear? And 1 or 0, this is 1 and we can say this is not, so this is 0. Clear? Now listen. Now if I writing this is 1 and 0 as my input, we can say this is what 0 and this one is 1. 1 or 0, this is 1 and we can say this is not, so this one is 0. Clear? Last one we are taking like this. Let's suppose we have 1 and 1. Clear? We are taking this is 0 and 0. 0 or 0 we have 0, this is 1. Clear? Now from here you can see 0 and 0 we are having two input and we are getting 0. 0 and 1 we have 0. 1 and 0 we have 0. 1 1 1. It means this is a truth table of AND gate. Clear? So directly you can say this NOR gate is behaving as a AND gate. Clear to everyone? So this is all about this question. So dear student, this is all about class 12 chapter number 14, Semiconductor, NCERT and exercise solutions. So definitely you have enjoyed each and every solution, and definitely these solutions are very fruitful to you in your upcoming examination, in your competitive examination. So like this, definitely we are grateful to you because you are connecting with us, and definitely a good future is awaiting for you. Clear? So this is all about this chapter. Thank you so much.